Okay, so here we are, 6th of November. Remember, the textbook is still there. And you can have some time today to finish off the last lab if you need it. But I really want to try and get through a few things today. In particular, I want to kick off the group project. I think that's the most important thing to do. And I hope it's clear that I've changed what we're doing as far as I'm not going to get people paired off with the project. We're all going to be doing it as a group. The class is small enough that I think I can get away with it. We'll see how we go. Oops. So, build a CPU. So what do I want to talk about today? I think most people have already taken the midterm, so I want to talk about what I was looking for in the midterm to everybody. I want to look at chapter 2 of the Zycle. I want to talk about building a CPU from a high level perspective. And then we can do the labs. Starting to build a CPU will take a little bit of talking before we get there. And I might have to do a bit of on-the-fly coding and git-hubbing and hitting on before we get there. One thing I haven't done yet is I haven't set up a quarters project. Right, so is it? Any questions so far? You all good? Thank you for getting here before the rest of them. Anyway, so the midterm. Let me talk about that. I have 12 people taken, and one person keeps making an appointment and keeps not keeping that appointment, so I don't know what's happening there. I've emailed several times. So the first 4 questions are basically background, right? There's basic stuff you probably should know from 363. But knowing it from 363 and being able to explain it to me is a different thing. And that's partly why I put it. Also partly just several of you haven't taken an oral exam with me before, so it gives you a relatively easy lead in. So what do I want? What a Carnot map is? Well, a Carnot map is a reordering of the truth table, right? And most people said that. Instead of having just a linear progression of the truth table, we've got a 2-dimensional version of the truth table. That's pretty much what it is. How to use it? Well, it's used for simplifying logic expressions, right? And you can, in the case of this particular one, the way you simplify logic expressions is you group ones that are adjacent. You should also mention that you can group don't cares that are adjacent to ones. You don't have to group don't cares, but you can group them with ones if it makes things simpler. The number of ones you can group are powers of 2. 1, 2, 4, 8, or 16. Obviously, if you grouped 16 ones on this particular Carnot map, that just says the value is 1. But that's okay, sometimes you get things like that. It also pays to mention that the expression you get out of a Carnot map is a sum of product expression, SOP. What else did I? yeah, that was pretty much it. So, explain what fan-out in logic is in logic circuits. So fan-out is the number of outputs that, number of inputs that a particular output can drive without the signal degrading. I was also looking for a range of values, right? And I wasn't particular about what range, but a range. Some people just gave me a single number, which isn't quite right. The range I would give is possibly 4 to 20. More likely it's 8 to 12, right? It helps if you talk about the voltage degrading, so back to physical quantities. Part of the reason why fan-out is important, or fan-out degrades the signal, is because a single output on a logic device can't pump out enough current to drive lots and lots and lots of inputs. So talk about the physics, both voltage and current, as physical quantities that are affected. I think everybody got what is an excitation table for a flip-flop. It's the minimum number of, or minimum settings of inputs that allow particular transitions to take place. Okay? And then I think everybody got the JK flip-flop. That's okay. It would be really great if you could tell me what that is off the top of your head without any information in front of you. So I might do that just randomly during the final. We'll see. And then questions 5, 6, 7, and 8 are the design questions. Right? And question 5, so the present states and next states, right? So here we've got, there we go, sorry. So if the present state is 0, 0, then the next state is just the line below it. Why won't it let me change? That is bizarre. Something bizarre is happening here. Sorry, I'm just going to kill that and start again. Maybe unplug that. Plug it back in again. And we'll try again so I can actually draw. See if that works. There we go. So 1, 1, 1, 1, the next state is 0, 1, so basically the next state is just the row below it. Now, what a lot of people didn't notice, so a lot of you did, but a lot of people didn't, is the fact that there are 4 1-1s in the table, right? And the trouble with having 4 1-1s in the table is, even though there are only 8 states, 3 bits can't distinguish between those 4 1-1 states. Right? So I was also looking for, in the present state, next state, for an augmentation of A and B. So not just having A and B, but adding C if you only thought that it required 8 states, or D, C and D if you figured out it needed an extra 2 bits instead of just an extra 1 bit. Okay. I didn't dock marks for that on this question. The question 7 about the number of bits is where that came up. As I think I explained to everybody in the feedback section of the oral, if you decided that you could do it using 8 states by just having a counter that goes 0, 1, 2, 3, 4, 5, 6, 7 back to 0, then the answer for question 7 was 3 bits. If you were forcing the states to change in this particular order, the answer was 4 bits. Right? So there's 2 possible approaches you could take, and they had different answers for question 7. Let's see, what else we got? So explain how you would use a table of present states and next states to design the logic. Well, you fill out that table, whether it's 3 bits or 4 bits, present state, next state. And if it's 4 bits, that means you need to have, and you decide to use JK flip-flops, that means then you need to augment that present state, next state table with a total of 8 other columns. J1, K1, J2, K2, J3, K3, J4, K4. Right, you start from numbering from 1. If you start numbering from 0, it starts with J0, K0. And then once you've got that augmented present state, next state table, you've got your J's and K's, you've got all the bits, then you can put together a Carnot map for each J or K column, and that'll tell you the logic that needs to go into driving that particular J or K column. You can use the excitation table of the JK flip-flop. Some people decided to use a D flip-flop. That's okay. Even though the earlier question sort of pointed you towards JK flip-flops, using a D flip-flop is okay too, provided you used it appropriately, and that was fine. And then the explanation about how it works, there were 2, right? If you forced the logic, the sequence to go in, the state to go in that sequence, then the idea is, okay, I have my 4 flip-flops, and I have to force the first 2, A and B, to go in that sequence in table 1. I just designed the logic using the J and K augmented pieces from the present state, next state table to drive each flip-flop to force it to go into that in that order. Right? So that's what I was looking for in terms of explaining. The other explanation is I designed a 3-bit counter to count from 0 to 1 to 2 to 3 to 4 to 5 to 6 to 7 back to 0. And then I put output logic on top of those standard counter states to generate the A and the B outputs that I was looking to show. So either of those 2 approaches works, and that's what I was looking for. Any questions about the midterm? No? Okay. And I had very few people do 10 and 11 at all. I would have thought 10 was a very easy 10 points. Maybe 11 was harder. Anyway. Okay. Let me just take a swig of caffeine. Okay. Let's go back to the Zybook. And in the original edition of this Zybook, chapter 1 and 2 were just chapter 1. I split it up into here. Right, so what we want to do with logic is we need to take our logic expression and we need to put that into hardware. And just because of cost, we want to minimize the amount of hardware we need in order to do something. Right, so the aim is to simplify the expression you got. And the first way of expressing this is, as I've talked about for a while, is sum of product. And I tend to favour sum of product expressions. Right? And what you want to try and do, if you're doing this algebraically, is to look for opportunities to simplify. In particular, if you've got the opportunity to OR J and not J together, right? Because J and not J ORed with not J gives you always 1. Because if one of them's 0, the other one's always 1. If one of them's 1, well, you're done. Right? So that's the aim with seeking. Part of the reason I like the Carnot map is it does this sort of stuff effectively for you. Right? There's no real algebra involved. Here's an example. It's another example. More examples. And all of the earlier examples are pretty simple, right? They're direct application of that J plus J or not J. But sometimes things get hard to see by hand or hard to manipulate by hand. And that's what this example is showing. And there's another example. I'm not going to go through the challenge activity. So that's why K-maps are useful. They allow us to effectively do algebraic manipulation of for simplification, but we can do it graphically, and a lot of people find that graphical approach easier than the algebraic approach. And there's a key line there, right? A K-map is a reoriented truth table. So AB, right? AB. So we're down in this corner. It should be pretty obvious. And what this piece is showing is that looking for that J or not J is effectively what you're doing when you're circling two adjacent ones, or a one adjacent with a don't care. And sometimes you need to cover a particular min term twice in order to get a simplified expression. And there's a two-variable K-map. And there's an example. And another example, which I'm not going to go through. Those examples were just of two-variable K-maps. You can also have 3, 4, 5, and 6-variable Carnot maps. You've all seen the 4-variable Carnot map, that was on the midterm. The 5-variable Carnot map is basically two 4-variable Carnot maps side by side, with one of them being E and the other one being E bar. Right? And the key there is when you've got two 4-variable Carnot maps side by side, if you circle ones in the same location in both E and E bar, that means you cancel out E in the expression. Right, there's a 3-variable Carnot map. 3-variable Carnot map. You get to 4 variables eventually, maybe? There we go. There's a 4-variable Carnot map. And the thing to remember is that this isn't just a square, right? It's actually a donut. Because this side, the right side, is adjacent to the left side, and the bottom is adjacent to the top. So if you wrap the top down to the bottom and then bring the left around to the right, you've got a donut. So that's effectively what you're showing here. That's why the yellow pieces here map, or can be, the yellow looping can be done because of that donut approach. And it looks like they've just got some more examples which we won't go through because I think you're pretty much good with Carnot maps. So De Morgan's law is very useful for manipulating algebraic expressions. Right? You can basically complement each variable and then change an and to an or, and you get the same thing, right? So here we have A or B all complemented equals A bar B bar, or AB all complemented equals A bar or B bar. So you can manipulate expressions that way. Particularly, you can convert from a product of sum type arrangement on the left hand side of the top one here, right? So this one here, you can convert from, that's a, I would call that a sum term, and you can convert it to a product term if you need to convert between sum of product and product of sums. And it's just more of De Morgan's law. It's okay. So the sort of gates that don't really fit into sum of product and product of sum are these: exclusive OR and exclusive NOR gates. And you're all probably pretty aware of those. And then the exclusive NOR is the same thing, except we've now got a complement bubble on the output of the gate. Here's what happens when you've got more than two inputs. Right? And notice the bottom line, right? What it's doing is it's saying I've either got an even number of ones or an odd number of ones. And here it's a 1, if there's 1, 1. 1, 1, or if there are 3 ones. If I've only got 2, then 2 ones or no ones, then the output is 0. Everybody know what a parity bit is? Yes? No? So, one of the problems with digital communications is you get bit flips, right? A 1 is received as a 0, or a 0 is received as a 1. So one of the big things that had to happen for digital communications to actually work is to look at error correction, or first of all error detection and then error correction. And the parity bit was the first way of doing error detection. The parity bit said, okay, here's the data, however many bits, and the parity bit would be set to 0 if we were assuming even parity, if the data had an even number of 1s in it. If the data had an odd number of 1s, then the parity bit would be set to 1 to make sure that everything that you received always had an even number, if parity was even. Parity could also be set to odd, in which case the reverse is true. If you had an even number of ones in the data, the parity bit would be set to 1 to make it an odd number of bits that you're setting out. I was fascinated when compact discs, yes I know an LP, first came out, right? I was doing my, I think I was a senior, I might have been a junior, and I learnt about what was happening with CDs. And one thing I learnt in my classes was that if there was no error correction on the CDs, they would sound much worse than vinyl. And the reason they would sound much worse than vinyl is you still got bit errors. And the trouble is, if you get a bit error in the most significant bit of an audio sample, that's a really big glitch. Right? And so the first attempts without any error correction were really bad. That's why CDs use a thing called Reed-Solomon coding in order to correct those errors. And even these things these days use quite sophisticated techniques on it to do to increase the likelihood that what you receive is what was sent. There's a whole theory about lattice codes and trellis codes that they use. But one of the first places where this sort of stuff started happening was with parity bits. So this section is about the universality of NAND and NOR gates. Normally when we talk about sum of product or product of sum, we think about 3 gates. We think about NOT, we think about AND, we think about OR. But in reality, if we have a NAND gate, we can do everything we need to do. If we have a NOR gate, we can do everything we need to do. Because, for example, if we tied A and B together, then we just have a NOT gate. If we apply De Morgan's law to this, let's see if we can go back here. Right, if we apply De Morgan's law, we can take our NAND gate and turn it into an OR gate with active low inputs. So it's pretty easy, I think, to eventually convince yourself that all we need is one of these or the NOR gate. So here's the let's just run through this one because I think it's important. Right, so if we connect both inputs together, we get a NOT gate. If we stick two inputs together on the front end and just have a NAND, then we get an AND gate. That sort of makes sense. Or if we just, based on my drawing before, if we just stick two NAND inverters on each input of another NAND gate, we get an OR gate. Right, so that should be pretty straightforward. Right, so all this is saying is we can use that De Morgan approach and can convert things, and when we get double NOTs, double complements, a complement on the output and a complement on the input, then they're not doing anything in effect, so we can cancel those out. Another way to think about it is to allow yourself to have both active high signals and active low signals, right? Remember here, this is an OR gate, but it's got active low inputs. It's a NAND gate, in other words. Muxes might be relevant. So a mux, a multiplexer, is a switch, right? And you can select which input of the switch goes to the output. And if you've looked at your assignment for today, one of the possible components we would have is a mux. Those muxes are a bit more complicated than this one, but still, there are two multiplexes, I think, in the slides that I shared with you for the assignment. The nice thing about a multiplexer is that it allows us to form all possible combinations of outputs. Right? So for this output, we can make any logic function we want of two variables just by tying the inputs high or low. Right? I could make an AND gate by tying I3 high and the other 3 low. Then we would have 0, 0, 0, 1, which would be an AND gate. I could do the opposite. I could tie I3 low and I2, I1 and I0 high, 1, 1, 1, 0. Now we get a NAND gate. Not quite the same thing, but very much related. In the FPGAs we've been using, they use what are called lookup tables. Lookup tables are almost exactly just a multiplexer, but instead of just having a dangling Y here, they have a memory, a 1-bit memory on each of these. And we can set those 1-bit memories, right? We don't have to force it high or force it low. We can just set it to 1 or 0. And so lookup tables allow us to do this same thing, generate any logic function we want just by setting, effectively writing the truth table into the hardware, which is kind of fun. And this is more about muxes. And there's an example which I won't go through. Right, so decoders are another interesting device, and they convert our 2 bits of input in this example. It's a 2x4 decoder, and we output a 1 only when we select that particular output, so the truth table is there. Right, so Y3 is really just and, right? I1 and I0. So that's kind of cool. That's the circuit for it. There's a slightly larger version, 3-bit version. Okay, we'll go through there. Encoders. Right, here we go the other way. Whenever we get a 1 on one of the inputs, we get that input denominated of the output. Just go through there. We've talked about don't cares, right? Don't cares, we don't really care whether it's a 1 or a 0. So we can use them or not in our function minimization, depending on what we're trying to do. And I won't go through that. I think we know that. The one piece I did want to go through in a bit detail in this chapter is this one, I think, in the next section. Right, so prime implicants and minimal covers. A function's onset is the set of minterms that define when the function is 1. Right, so remember what a minterm is? It's all of the inputs ANDed together, whether it's complemented or not. But there's just one of them, but they're all there. A term covers a minterm if the term evaluates to 1 whenever the minterm does. Right? So the term AB covers the minterm ABC. An implicant of a function is a term that covers only minterms in the function's from set. Right, so for this function here, AB is an implicant due to covering ABC and ABC bar. So ABC bar and ABC. So AB is an implicant that just covers those two. So on a K-map, each of the ones represents a min term in the function's onset, and each valid circle is an implicant. Notice it says not necessarily the largest, right? We haven't got to largest yet. We need to modify the name implicant before we can get to the largest covering. So let's have a look at this one. Right, so there's the onset. And there are all the ones from the onset. There are 1, 2, 3, 4, 5 midterms. So there should be 5 ones in the K-map. So then we can form our implicants. Right, so we haven't done anything really sensible yet. We're just defining terms more than anything else. So it wouldn't make any sense to write this function f as a, b bar, c bar, a bar, b bar, c, a bar, b, c, a, b, c bar, a, b, c, a, c bar, a bar, c, a, c, a, b. Right? It makes no sense. So we need something else to tell us what we've all been doing, but we need something else to tell us how to choose which of those terms to use. And that's all just stuff that I think. Here we go. So now we can modify the term implicant with the word prime. Right? So a prime implicant of a function is an implicant that cannot have a literal removed without becoming a non-implicant. On a K-map, each largest possible valid circle represents a prime implicant. Right, so here A bar, B bar, C is an implicant, but it's not prime. There's a prime implicant. And there's some more. So now we need to do some more modifications. Right? A minimal cover is useful to create the smallest circuit for the function. A function's minimal cover is an expression for the function having the fewest terms, each with the fewest literals. Right? So we want to minimize the number of terms we all together, and we want to minimize the number of literals in each term. So we defined the prime implicants, and that was useful. And then on a K-map, a minimal cover is a cover using the fewest, largest circles and largest circles of prime implicants. Now we have another modifier, essential. An essential prime implicant is the only prime implicant to cover a particular min-term in a function's onset. Right, we can do lots and lots of coverings, but an essential one is the only one that covers that particular one. And an essential prime implicant must be in the function's cover. So here's the way you think about it. Generate all the prime implicants by drawing the largest possible circles. Add essential prime implicants. Find any essential prime implicants and add them to the function's cover. Select prime implicants to cover any ones not covered by the essential prime implicants. So let's see that example. Right, so each of those is a prime implicant. So the orange circle is the only one that covers the bottom left one, and the red circle is the only one that covers the top right one. Right? So both of those are essential prime implicants. And then we just need to figure out how to cover the 1 at 1, 1, 1. Right? We could do it either using the purple or the green, but only one of them for a minimal cover. So I do want to have a talk about the Quine-McCluskey algorithm. I haven't covered that previously, and we need to talk about it. However, let's just see, I think it's next. What I'm going to do is I'm going to take a 10-minute break before we do that. Then I'll go into Quine-McCluskey because I think it's important. And then we might start talking about CPUs and Git and labs. Any questions so far? Okay, let's take that 10-minute break. And we'll have a look at Quine-McCluskey afterwards. Yep. I'll be right back. so we'll start shortly. I'll wait until we have 4 or 5 people still going. We'll wait until they're back. But so far, we've reviewed the midterm, and we're just about to finish reviewing chapter 2 of Bizarre. Okay, so one of the problems with logic minimization using Carnot maps is it's a little error prone, right? You can have what you think is a minimal cover, but you've accidentally covered one term twice that you didn't need to. What Klein-McCluskey does is it lets you effectively prove that you have a minimal cover. So that's useful. Right? Let's just read. Klein-McCluskey is an algorithm for 2-level logic minimization suitable for computer automation, and it's a tabular method rather than a graphical method. And the steps are, first of all, generate the prime implicants, and then pairwise check the minterms for I and J or J bar opportunities, and combine the new terms into a new column, repeating with new terms until no more combinations could be made. Each term that wasn't combined with other terms is a prime implicant. Right, so that's the first step allows you to find those prime implicants. So then step 2 is find the essentials. Draw a table with prime implicants as rows and minterms as columns, putting a mark to indicate a prime implicant covers a minterm. For any column with only one mark, the prime implicant for that row is essential, and so is added to the cover. All minterms covered by that prime implicant are also checked off as covered. And then once you're done with that, then you need to select cover any remaining ones, and you select minimal unadded prime implicants to cover those remaining terms. So here's an example. Our onset is 0, 1, 5 and 6. So there's 0, 1, 5 and 6. And we check pairs. Right? Now we check the pairs with the second term, and then we check the pairs with the third term, and then we check pairs with the fourth and last term. Right? So now we've effectively given ourselves a checklist to make sure that we check all of those minterms for that I and J or J bar minimization. Okay, now we've got to do it again, but this time with the next column. And we check to see if there's anything else that we can do. And it turns out there's not. Right, it's possible. This is only a 3 variable problem. If we had a 4 variable problem, it's possible we would get another column out of this. And if we had a 5 variable, you could get even more columns. Right, and now we take all of those prime implicants and we check which of the min terms those cover. If there's only one mark in a particular column, that gives us a prime implicant, an essential prime implicant. So we copy those over, and any other min terms are covered or are also crossed out. So here we get A bar B bar or AB in this step with the essential prime implicants. And then we've got to cover min term 5, so we could do it with just that one, with B bar C, or we could do it with AC. Either one of those would do. Right, it says, well, it's a bit low on the screen. It does say that choosing, we didn't have to choose the green one, we could have chosen AC as well. But only one of them, not both. Right, and here's the same thing, but done using Carnot maps. And you could do the same problem using Carnot maps, no problem at all. The issue is just it's a little less clear with the Carnot maps. You don't have it as effectively a checklist, which is what Klein-McCloskey lets you do. And yeah, let's. So I just went through Klein-McCloskey. And what does it want to say? So one of the things that we could have done, and which you should do in a larger problem, is instead of just writing down all the min terms straight away, you order them so that they only differ by 0, 1 or 2, right? The number of uncomplemented pair literals, right? So A bar B bar C has one uncomplemented literal, while ABC has 3. And that way, if you order them that way, it's easier to check to see if there's opportunities for this I and J plus J complement. And I was interested that they have a cop-out for the for Petrick's method. Right? That's step 3. Let's go back to Klein-McCloskey. Right? Step 1 was generate the prime implicants. Step 2 was find the essential prime implicants. And then the step 3 is cover the remaining. And as we saw in the example, right, to cover the remaining, they chose B bar C, but we could have also chosen AC. And that last step, that's step 3, finishing off the cover, has another way to do it, or an algorithmic approach you can use called Petrick's. And it's a little complicated, so I'm not going to go through it. But it is kind of interesting. There's an example there on Wikipedia that is kind of interesting. Okay. So I am done reviewing chapter 2 of the book. I'll look at chapter 3 next week. I'm not quite sure what to do next as far as looking at building a CPU. I do want to do that. I'm not sure how it's going to work, because we have, what have we got? 4 and 6. We got 10 people. We're missing 3 maybe. That's the best. Anyway, we'll see how we go. So let's just go on to my CPU slides. Right, you probably have seen this diagram of the internals of the CPU. Right? And one of the things I wanted you to do, in fact, let me just, if you haven't already done it, please, I think I made it. I don't think I made it close. I made it due this morning at 9, but it's, if you haven't already gone into the assignment for some grabbing this, please do it later on this morning. But at a first stab, I would say we need a 16 mux, registers, a program counter, and an ALU. There's other stuff we need. I've been thinking far too much about this, and one thing I might look at doing next time I teach this course is in this one I talked about we need inputs and outputs, right? I'm wondering whether it's going to be possible next time I do run the course to add video output to our CPU, so we can connect it up to a monitor or to the projection and show what the thing is outputting. I'm also wondering whether we can connect a keyboard up to it, so we can have it won't be a real CPU, but a real computer, but it will have video and it'll have a keyboard. I think we should just restrict ourselves to inputs being the push buttons on the device and outputs being either the LEDs or the 7-segment displays, or the buzzer if we want to make the buzzer buzz. So one of the problems is that we need to define an instruction set, right? What's our CPU going to do? And the NAND to Tetris people have defined 2 different sorts of instructions. A instructions, which is just used to set the A register. Remember, we have an A register, which is here, and a D register. And the A instructions just allow us to load data straight into the A register. Right, and you can see how that's happening, right? We're getting the instruction, right? There's our instruction, and it's going into a mux, and if we have an A instruction, that mux is selecting this input to route into the A register. Okay? So all the A instructions do is they're identified by having a 0 in the most significant bit, and then the value is just the remaining 15 bits. Okay? So we can only have a value between 0 and 2 to the 14 minus 1. So a 15-bit value. Oh no, why is it not synced? It's there, let's see if we can sync it properly. I don't know why it does that to me. Yeah. If you ever write software, if the software says sign in and there's a sign in button, allow the person to sign in when you click the sign in button. You don't want to have to go into settings, etc. Let's try that again. It looks like it's syncing this time, and it's got a little check. It had a little check earlier, which I thought meant it was supposed to have all of the slides. What's odd is I put all the slides in at the same time. So how it only got some of the slides, I don't know. Okay, sorry about that little rant. So the other sort of instruction are C instructions. And these are a lot more complicated. The easy part is that they're identified by having a 1 in the most significant bit. In this particular case, it's actually simpler than it could be, because the next 2 bits don't mean anything, right? And they've just selected them to always be 1. And then there's 3 groupings of the remaining bits. There's the control, there's the destination, and there's the jump. Right? So each C instruction can make a change in the data. That's what the computation piece is. It can tell you where to put that data. That's the destination. And it can then do a conditional or unconditional jump, or no jump at all. all into one 16-bit word. Right, and here's, let's just scroll it up a bit so we can. Right, so in the computation, we've got the first three there are just allowing us to do 0, 1 or -1 easily. And then the next one is telling us, okay, nothing if the A bit is 1, but D if the A bit is 0. Then we can select between A and memory. Then we can select not D or not A or not M. Then we can select -D, -A, -N. We can increment D, A and M. We can decrement D, A and M. We can add A to D, we can add M to D. We can subtract A from D, we can subtract M from D, etc. Oh, you can read this as well. So. But they're all just setting up the what the processor does based on the instructions. So the program that you would write for this computer is just a sequence of 16-bit numbers. And I would call this probably machine code. There's no assembly. If you look at the NAND to Tetris book and website, they actually have an assembly language, right? For the A instructions, they have an assembly language that says, okay, if you see an @ sign followed by a number, then that's an A instruction. Okay, so @15 will load 15 into the A register. And the different jump conditions: jump if greater than, jump if equal to, jump if greater than or equal to, jump if less than, jump if not equal to, jump if less than or equal to, or just jump. And I'm not quite sure, now that I think about it, where it's getting the jump to information from. I assume it's coming from either the A or the D registers, but we need to figure that out. Any questions about the processor that we're going to do? Right, that's what we need to have it do. We still need to get all the bits and pieces together. And what I want to try and work the way I've been asking you to work, but we've got to iterate a little differently. Right, this week I want to plan, meaning designing the components, and we'll do some of that just here with me on the screen. You're going to have to implement the components, and then we're going to have to write a test bench to test the components. Normally what we've done so far is we've had a single test bench per project. What we're going to have to do now is have multiple test benches in the project, so that each individual component, the register, the mux, the ALU, all has its appropriate test bench. Okay. That's what I'm want to try and start this week and maybe finish this week. Next week we're going to hopefully have some working components, and we need to think about how we integrate them. Right? And I'm not sure yet what the top level entity in the Quartus project should be. Right? Maybe it should be just something called CET 466, because it's not going to be just the CPU, it's going to have to also deal with the I/O, the input components and the output components. And we want to test the top level entity. And then I'm hoping, maybe not in 2 weeks' time, but maybe 3, or actually it's probably a little longer given that we're coming up against Thanksgiving. But I'm hoping that in the last week of semester at least we'll be able to try and deploy it to the board. Maybe write a program and test that program runs. Now that could be entertaining, I think. So this is what we've got to do today. We've got to put together a Quartus project. I have yet to put together a Quartus project. As I think you saw, hopefully. I want to talk about that too, so let's just open that in a new link. Right, so let's make it bigger so you can read it. Right, so here's the repository, and at the moment it just has the README file, which doesn't say much. It's got chapters 4 and 5 of the NAND to Tetris book, as well as the slides from that book. And it has one subdirectory called VHDL, which is where I'm hoping to put all of our Quartus stuff, but I've only added the debounce switch implementation that I put together. Right? So that's there. But what I want to try and do soon is put this together. Put a Quartus project in here. Now, there's a few things, ground rules that I want to get through before I fire up Quartus, and I'm not sure how that'll go. But let's go back here. So one of the things that I talked about earlier is this. This is what's called a Kanban board. And it's basically an indication of what work needs to be done and what state that work is in. And there's only one task on it at the moment, decide on components. That's your assignment for today. That was your assignment for today. The other columns, there's backlog. That's going to be a list of all the stuff we could possibly do. There's consideration. That's stuff that we're going to do, but nobody's taken it on board yet. Being worked means somebody's been assigned to do it, and they're doing it, or they're about to start doing it. Once that's done, it moves over into requires review. Now remember, plan, do, review. I'm not sure what the right thing to do is, but if you're working in a company, if you produce a product, you are not the person that tests that product, right? It's usually given to quality assurance, or sometimes another person, another engineer, or another programmer, or it's not you, right? Because you could say, "I've done it. It's perfect," and of course you never see the flaws in your own children, right? So you want once the task has moved over to here, you want somebody else to review that. Once it has been reviewed and it passes all the reviews, it moves over to done. If it doesn't pass the reviews, it usually gets kicked back to consideration, and there needs to be some explanation as to what's wrong. Then somebody can pick it up, maybe the person who worked on it before, or maybe somebody new, and can move it over to being worked. Does everybody mostly understand how that works? Yeah? I'm going to cut that out, and it is a Kanban board. Yeah, it's a Kanban board. So let me just put this under the project work section in Blackboard, so you know how to get there. Okay, so hopefully that fires up appropriately and everybody has access to it. If you don't have access to it, let me know and I'll figure out what the problem is. Okay, so that's the first thing about how we work. I also want to talk a little bit about how Git works. Right, for a start, in order to get a copy of the repository, you need to do something like this: git clone, and then either the HTTPS URL or the SSH URL. Right, to get the SSH URL, you need to have set up a key with the repository, and if you want to do that, I'll show you how to do it. You may not be able to do it on these computers. I'm not sure whether that gets installed with Git or not. However, if you do clone it using the HTTPS, you will need to set up you can't use your GitHub password, you have to use an access token. And you can get the access token from the settings, developer settings, in the GitHub website. At the moment, the repository has two branches. It has main and it has, I think it's CCSU consumers. What should happen is whenever you do new work, you do not do new work on main. You never add anything straight to main. What I want you to do, and I'll give you an example of how to do that shortly. What you do is you make a new branch. Right? And a branch is a complete copy of the current state of the repository. And you do it by saying git checkout -b for branch, and then the name of your branch. I want you to use your GitHub handle as the name of your branch. If you decide you need a different branch, then I still want you to use your GitHub handle in the name of the branch, but maybe append a 1 or a 2 or an A or a B to it, so you can distinguish. And you go ahead and you make changes, and then you, on the command line, you say git add and add the names of the files that you've changed. You can do a git status to see what Git thinks has changed, and it'll show you the red stuff that hasn't been added and the green stuff that has been added. And then you do a git commit minus n. I usually like to have a -n, and then some message about, just a one-line message about what you changed. What did you do? As a shortcut, GitHub allows you to say you're done with stuff by putting numbers into here. So for example, let's go back to the repository. Right at the moment, that task on the Kanban board is an issue. And here it's just called decide on components. This issue is issue number 2. Right, so it says number 2 opened 6 days ago. Right, decide on components. If I commit to GitHub and I say fixed number 2, this will be closed. Right? I'd rather you didn't do that because I want to move it through the Kanban board and close it from the Kanban. But you can do it that way. Once you've committed your changes locally, that's only changed the local copy of the Git database. It hasn't changed what's on GitHub or wherever the remote database is. So you need to push those changes back to remote in order to do that. And usually it's just a git push. Sometimes you need to do a -u remote origin or something like that. But usually just git push. Sometimes somebody else has changed GitHub before you have, and the git push will say, you can't do this. So usually what you can then do is do a git pull, which will get the latest changes, integrate it without you having to do anything, hopefully, and then you'll be allowed to push up. If there are conflicts, git pull will tell you that there are conflicts. If there are conflicts, feel free to try and resolve them, but if you haven't used Git before, you're in for a little bit of time. Get in touch with me via email or via Discord is the easiest to try and resolve such things. And this was just a note about it doesn't let you use passwords, and this is where you get a personal access token. Right, settings, developer settings, personal access token. So this is what I get if I just click on my avatar. Settings down here, and then I missed a slide, but there's a developer settings. Click on developer settings, and then the bottom option is personal access tokens, and that'll generate a number or a token. You need to store that token somewhere. You can use it immediately and it should remember it on your machine. But if you, for whatever reason, nuke it on your machine, you'll have to regenerate another one because you won't be able to see it again after the first time it's there. Just for security. You can delete it and generate another one. That's okay. But I think that's all I want to say about that. Any questions about how I want to work? No? So you will make mistakes, I guarantee it. Just try and figure out that you have made a mistake and get in touch, and we can sort it out. Huh? So let's do that. So I think what I want to do next is fire up quarters and see about see if I can clone this. Okay, that looks okay. It got access to the private repository, so that means it's probably okay. It doesn't like me. So all I want to do is I just want to check that I can push back up to the repository without problem. CET466. There's the GitHub repo, and I'm just going to open. .md stands for Markdown, right? It's a simple formatting system that lets you, that GitHub uses, and in fact a lot of places use. Stack Overflow uses it as well. Okay, so so what I can do is I can link to the components, sorry, to the so there's a change that I made, and now I can do a git status, and you should see it in red there that I changed the README. And now that I've added it, it should change to green, and I've done that. And now I can commit, and now I can push it, and that's gone all the way back up to here. And if we go to the code tab and look at the README file now, right, you'll see that we have a link there called determine the components, and it takes us directly to that decide the components thing. Okay. Why am I showing you this? I want you to document what you do. I want you to make markdown pages so everybody can read what's happening. So part of your grade for doing anything in this group project is whether you documented stuff, whether you had a .md file. Right? If you make a .md file, we'll have to decide exactly how it shows up here, but you should link to it from this readme.md file. Right? So that everything's accessible from here. We'll figure out how to do that appropriately. Okay. So we've got determine the components, where we've got to. Let's open that up. Right, so I started us off on this assignment to say we need a program counter and a switch debouncer. And then Bright came in with clock and ALU. I'm not sure clock is necessarily a component. We may want to slow down the clock and have a clock divider. Right. But the clock itself, we probably just want to use the onboard clock. We could also use one of the switches as a clock, in which case we probably want to debounce it. And I think we've already put a debounce. Right, and then we have Mohammed has buses and registers. Certainly registers. Buses are more like just, static logic vector 15 down to 0. Right? They're just a variable. So I don't think they show up necessarily as a component. You might think about them as a component though, is in the top level design, the top level entity, right? Because you've got to link it all together. And maybe that linking it all together includes some signals that route things appropriately. Right? Then Fahim has storage and memory, right? So the original diagram there has a ROM and a RAM, right? So we probably want something like that again. And then Matt has mux and a cache. So I would love to think we could have a cache on this, right? But the reason you usually have a cache on more advanced processors is because getting data out of RAM and into the processor takes too much time for the really speedy, 4 gigahertz, 6 gigahertz CPUs that we have on these things. So you need to preload stuff into the cache so that you can get access to it really quickly. We're only running at 50 megahertz, so I don't think we're going to need a cache for this one. And then Emily has a control unit, instruction set, and some type of reset. Instruction set isn't really I wouldn't call that a VHDL component. We certainly need to decide what the instruction set is, and then it needs to be encoded. And then Kevin says control unit ALU clock address register. and David has clock system, which is more like what I would think. It's not just the clock, and ALU and data and addressing registers. And then Eric has clock, ALU, mux 16. And Anas has program counter and output components. And Michael has the status register, status pointer, clock system, and instruction set. And that's all we have. So let's go think about what that means. So I'm going to create I'm just going to call it component mux 16. Right, and each of these tasks has three pieces: design, build, and test. Right, so the build means write the entity and architecture in VHDL. Test means write the test bench that tests it. Right, so register is another one, and I'm going to call it a 16-bit register just so that we're clear. I think we had program counter, input, output. So design, build, and test. And again, it's a 16-bit program counter. Now let's do the memory. And in this, I'm going to add that you need to have a test program. Okay, so we may have to leave this one until with more of an integration test. Maybe. Maybe not. Okay, remember that diagram had the ROM and the RAM, so we've got to build a RAM component. Right, so far we've got the mux, we've got registers, we've got the program counter, We haven't got the ALU yet. And I didn't include the ROM and the RAM diagram that's in the... so we need to add an ALU. Now this one is going to be a pretty big component, so I'm not sure how we should tackle that. We may have to subdivide this into something a little bit easier, but we'll see how we go. Now the other two components that I can think of, at least basic components, are the input and the output. Right, so take input okay, and then the output. And I might put two separate ones, one for the LEDs and one for the 7-segment displays. It's possible we want to make the buzzer go. It's possible we want to do other stuff. Let's just leave it there now. So now let's have a look at what we've got. Right, we've got all those things. Let's see if they show up here. I don't know whether they show up here. So let's, I don't know how to make them show up here. That's no good. Maybe I shouldn't have done it there. I should have done it. I'm going to have to figure that out. Oh well. Ah, there we go. We got to put it there, and let's. There we go. And we'll put it in the backlog. Right, I'm gonna do that offline. I'll put all of them. I'll add them all there. So now we should have. Yeah. So there's our backlog. Component output displays is there. Okay. Hi.
You've got a regular class here, right?
Yeah, I've got a class here. So, yes, apparently one of the other faculty was told to come in here and wait for all the open house students to show them around the lab. It could, I mean, I don't know whether they want to sit through one of my lectures as just being an introduction to the university. Anyway. Okay. So we've got the components, mostly. Now we've got to go and do the design. So let's do what I suggested. And let's make that quarters project, right? So I'm going to make a new project. See if I remember how to do it. And I'm going to put it in the VHDL directory. Right, I'm going to put it there. What is the name of the project? Let's just call it CET 466 CPU. And for now, I'm going to leave that as the same as the name of the top level entity. Right, I'm going to use an empty project. Just because I know it's there, I'm going to add the debounce switch. Okay? So I've added, so the Quartus knows about the debounce switch. And then I need to select the C8, that one. And then my simulation is Model Sim Altera, and my language is VHDL. Actually, just a complete aside. You would have noticed there, right, in that drop down, there's VHDL, which is what we're doing. There's Verilog, and there's system Verilog. And it's really bizarre, but one of the things I do to keep from getting bored is I help out with intellectual property disputes, right? And sometimes I get to see this stuff. And some of the ones I've seen actually use all three languages, right? Because their compile systems can compile all three languages. Just Quartus can, right? Sometimes they have something that they know works in VHDL, so why rewrite it? Use the VHDL component, provided you can get access to it. The nice thing about VHDL is it's a strongly typed language, right? You can't just assign variables willy-nilly like you can in Python or PHP or something like that. In fact, one of the bad things about VHDL is it's a strongly typed language because you can't assign different variables from different types to each other, right? One of the nice things about Verilog is that you can assign different types across to each other. And again, one of the bad things about Verilog is that you can assign different types, because sometimes that's not what you want. What system Verilog adds to the mix is it takes bits from VHDL and from Verilog and from C and from C++, and lets you do very complicated languages. What the proponents of system Verilog say is that it's not just a hardware design language, it's a hardware design and verification language. With Quartus and VHDL and the test benches, you have a verification mechanism, but it's not built into the language. Whereas System Verilog, the ability to do verification testing is built into the language. So, bit of a tangent, but I thought I should just mention it. And there we go. And hopefully that'll show up. Wait for that to fire up. Okay. So we want an entity, CET 466, CPU is, and entity CET 466 CPU. Architecture, CET 466 CPU arch of CET 466 CPU is begin end architecture. Architecture CET 466 CPU arch. But I don't know whether that's the right thing to do, but there we are. I haven't put any inputs or outputs, so that's obviously the wrong thing to do, but at least we've got something started. And let's see how badly it works. In fact, before we do that, let's go back and see what we've created. Right, so the only thing so far we've created is a QPF file, a QSF file, and a VHD file, and a DB database directory. I suspect all the other files that Quartus generates don't need to go into the repository. So what I'm going to do is I'm going to add those 3 files to the repository. Uh, 466 CPU.star. Oh, it's in VHDL. Let's try that again. Okay, so now they're all green and I can commit them. So now there's a Quartus project. Now let's see what happens with the compilation. One of the things I try to do before I commit is to make sure everything compiles. I didn't do it this time because I wanted to see what intermediate files Quartus produces. And hopefully we'll get there. Just thinking about it. Okay, so we got an error, at least one error. Near text architecture expecting semicolon. Oops, I forgot a semicolon there. Don't you hate that? Let's try that. We'll try it again, see what happens. Right, so now we should see here, I don't think I pushed. Did I push? I did. Right, so there's the Quartus project. So now when you clone the repository, it'll come down here. Still thinking about it? So I think we should figure out who does what, or who is at least starting to do what. And let me just reset the list of students. What I'm going to do is I'm going to get ask the first person which component they want to have a look at, and I will assign you, provided you've got you've accepted the GitHub invitation to join the project. I will assign you that item in the list. And first up is Michael. Any thoughts on which of the components you want to try and look at?
The easiest one.
The easiest one.
Most simplest.
The simplest. Let's go with the mux. I don't know which is the simplest. Honestly, I don't.
Can we take a look at the list again?
Sure, we can do that. Maybe the 7-segment displays, right? Output LEDs, input switches. I would avoid the ALU for now, everybody. RAM, program memory, program counter, register, mux. Is mux okay, or do you want a 7-segment display? Output LEDs?
I'll do the display.
The display?
Output display.
This one here? Okay, so let's see if we can see you in the list. There you go. And let's see if we can put it on the board. If I remember how to do that. I already put it on the... Right, where is it? There. Okay, so there's your assigned thing, and I'll move it out of the backlog. What I want you to do, Michael, is once you we break up to do the labs, see if you can move it over to being worked so that we know you're working on it. Okay? Next up we have Mohammed. You can see the list. No, you have to remember the list. So anything that's not assigned: output LEDs, input switches, RAM, program memory, program counter.
How about registers?
Sorry?
Registers.
The register? Okay. You want to have a look at that one? We could do that. So let's grab that one. And there you are. That's assigned to you, and now I have to put it on the project, don't I, to get it to work. Yeah, so that's on the project. Let's just check to see. I didn't put it in a particular. It's a waiting triage, so I'm going to put it on consideration. Again, once we break up, if you can move it into being done, that would be good. Okay. Michael's not here. He's getting the ALU. Enough. Let's get the list up again, shall we?
What's the output LEDs into?
Output LEDs?
Is that just LEDs?
Pretty much just LEDs. Yeah? Want to try that one? I can make it hard, don't worry. And I'll put it under consideration. Okay. Matt, you're next. So, let's wonder if we can assign to nobody. So I'll get rid of all the ones that are already assigned. So we have input switches, ALU, RAM, program memory, program counter, Mux 16.
So I'll try the mux.
Try the Mux? Okay. That shouldn't be too hard. So there we go, there's Matt. And we'll put it on the project while we're here. Put it there. Now go back to the issues list. Bright isn't here. Charles isn't here. Kevin.
I'll take the program counter.
You take the program counter? Okay. So let's give Kevin the program counter. add the project. Okay, there we go. So I don't have much left. Let's see who's next. David. Program memory? Okay. And let's get the assigned to nobody list. So we got 3 things left. And Michael G. Input switches. Okay, you can do that. Emily, you're next. Let's get the pieces. So we really only have RAM or ALU. So what I suspect is going to have to happen is we're going to have to do a few iterations of the ALU. So feel free to take it. I think, but just because it's big, we can break it down into bite-sized chunks. Okay. Okay. Now we just have Fahim and Eric to go. So Eric, you're up next. So I suppose you're on the RAM.
Yeah, I guess. I'll take it.
Yeah. And Fahim, what are we going to get you to do? So, well, so one thing the other component I just realised I forgot to add is the top level entity. You'll take that one? Okay. So so Fahim, I'm going to add you onto the RAM.
Unless you want to.
And I'll create another one for the top level entity. So we'll put Fahim on that one. Okay, and then I need to add another so you may not have much to do initially, but you can certainly start thinking about how to connect everything up. Okay. Okay, let's just triage that to get it onto the board. Okay. So I've got to do that. Everybody should have something in that list. I'll talk to the people who haven't been here. Michael and Bright and Charles. What I might get them to do is look at
Make them do the test benches.
maybe test benches and maybe integration, which is sort of test benches as well. Maybe writing a program, right? I think that would be also something useful. So for next week, what you all need to deliver are 3 things. A branch with your handle in GitHub. Inside that branch with your handle, there might be other things, but there need to be at least 2 other files, 2 new files. One file to implement the component, a VHDL file, .vhd file, in the VHDL directory that is aimed at implementing your component. Don't worry about test benches just yet, and if you feel like it, you certainly can, but don't feel obliged to do it just yet. The other thing I want you to put in there is a markdown file that documents what your component is doing. Right? It's a .md file, just like the readme.md file. You put a hash at the beginning for a headline, a double hash for a subheadline, triple hash for a sub-subheadline. You can put in links. You probably won't need any links. You can put in some formatting. I'll try and remember to send a link to the markdown guide. That all sound okay? Let me just check. I think that's all I wanted to do for now. Any questions? Okay. So before we split up, let's just check what happened with quarters. Okay, it's okay, it gave an error, but it's just saying that there's no logic in the top level entity, which is hardly surprising. But let's check what it created. So it changed the QSF and VHD file, and it made another directory as well as the DB directory. It made the output files directory. It also took a backup of the VHD file. I don't like having backups inside my Git repository. So what I'm going to do is I'm going to go into the VHDL directory. If I could type CD, that would be wonderful. And I'm going to create what's called a .gitignore file. Let's see if I can scroll that up so you can actually read it. Right? I'm going to create a .gitignore file, and I'm going to put star.back as one thing in that. BAK. Now, if I do a git status, that backup file Git no longer cares about the backup file, but it does care about the .git ignore. So and I'm not going to put the DB or the output files there. I suspect what I should do is put output files /star into the .git ignore. Maybe DB, I'm not sure whether I should put DB in there or not. Anyway, let's put it in. But I may change that depending on what happens. Okay, so now you can go and start your own. You've got to clone the repository, you've got to create your own branch, and I would suggest just making a completely blank component.md file. So, Michael?
So on Git, how do you make it so you don't have to log in constantly when you get push?
If you get that access token, then I'm still, I think. No, I've forgotten what the. Let me see what my remote is. Yeah. There it is. Let's see if that tells me. Oh. That's interesting. I've set up, it looks like I've already set up a key. Okay, so what you've got to do that, let me get out of here. There it is. So what I did is I created these two files. These two files, the idrsa.pub is your public key. the IDRSA file is your private key. What you need to do is you need to generate those two files, and I'll show you shortly how to do that, and then tell GitHub wrong one, where's GitHub? There's GitHub. Right, under settings, this is under my account settings, and under SSH and PGP keys, right, there's the SSH keys. That's actually the key that I started back in 2010. I probably should change that, but that's on my machine at home. This is the key that I'm using on this machine. And basically all you do is you say USSH key, and you cut and paste the information out of the, I think it's the pub file, but let's just see if we can have a look at the pub file. Type. Okay, there's my public key, and I just take that public key and I add it to where I showed you in GitHub. Now, how do you generate those? You should be able to do something like SSH keygen. Now, sometimes these don't quite work on Windows. Before I do that though, I don't want my keys to get clobbered. So I've made a copy of them there, right? So so now I just type SSH keygen, and it asks me where I want to store the file. I'm just going to say, call it IDRSA2, so it doesn't clobber my current one. Hopefully that'll work. I don't tend to use a passphrase. And now you should see that there is an IDRSA2 and IDRSA2.pub. What we can do is we can have a look at that. It's the same form but different letters, and all you do is you cut and paste that from here up into wherever it got to, adding a new SSH key into that. You give it a name, and then that should work. What I'd suggest is see how it works on these machines with you. I'm not sure how that's going to work, but let's try and get over it today, and then we'll figure out what the right thing to do is. Does that answer the question, Mike? Yeah? You're welcome. Okay, I'm done. So, 3 things: a branch, a VHD file, and a .md file. I will write up an assignment in Blackboard so that the people who aren't here know about it too. and we can go from there.
That's good work.
Yeah, no worries. Thanks. Branch. PHP.
Professor, so I'm gonna do everything at home on
Okay.
my local machine, but I had a question unrelated to this class.
Okay.
It's about the post that you, I mean, if you can talk right now.
Yeah,
It's gonna be real quick. So you remember the post that you sent inside of our chat, the home security chat?
Oh, yeah, yeah.
In regards to post with modulation?
Yeah.
So basically, I just wanted to know what's considered analog signal and what's considered, I know it's digital, but what would be considered analog? That's something physical, like external from?
Why?
Because remember how I said, for example, the toggle? So what type of signal would that be? Since I'm sending it to the server, would that be analog signal? Because the numbers is varying.
Right. So the stuff that's coming out of the app is going to be a digital signal, right? It's not analog. It's not a continuously varying voltage. For me, an analog signal is a continuously varying voltage.
Like a potentiometer?
Like out of a potentiometer,
Okay.
right? Whereas a digital signal, if it's a voltage, is either 0 or 5, 0 or 3.3 or 0 or 1.2, whatever the logic high voltage is. It's only those two values.
So what would you consider then? So the values, so the toggle that I have, that I showed you on the webpage that I created, is from 1,000 to 2,000. So what would, as I'm increasing, the values obviously increase, but what would that be considered as? A digital signal being sent to the server, or would that be, like, that's where I'm confused.
Right, so it's not, it's a completely sort of computer signal. It's not a voltage at all.
Exactly, so are you thinking it's a digital signal then?
Yeah, it's a digital signal.
Okay. That's where I'm just confused about. Because the link that you sent me is perfect, but I just got to get over that confusion.
Right. So you're going to get a number, and as you said, between 1,000 and 2,000. I think that PWM needs an 8-bit number between 0 and 255. Right? So you're going to have to map 1,000 to 2,000 to 0 to 255. If that's the right thing to do.
So I tried something yesterday, which was cool. I had a circuit that I made with the server. Let's just call it the ESP32 for now. So so using my app, I basically was toggling the toggle. So I had an LED circuit connected to the ESP.
Oh yeah.
And I'm toggling the range on my phone, and I could see the light flickering as I toggled. And then I measured the voltage. It was weird because as I was increasing the toggle, the voltage was just all over the place. So I think I'm on the right track because as I was toggling, it was doing movement, but I think I have to map it like you said.
Right.
Like from 0 with 8 bits, basically.
Yeah.
8 bits. So
Exactly.
So I found out to be coincident. I'm like, okay, that's
Yeah.
one step closer.
Again,
So,
take a video of it.
I will. I'll take you, Professor.
You're welcome.
So I was in here last week about lab 7. You're saying like you can submit like anytime we finish it.
Anytime until, I think I actually did set a due date sometime in December. Get it done, but it's not due today.
Okay, and also with the GitHub, like, do you mind if I try to do it on my own? Because I never used GitHub before, and instead of like using, I want to play around with it and try to.
That's okay. I do eventually want to get it into GitHub.
Okay.
And if you want to wait until next week to get it to GitHub, we can do that.
Yeah, I'm kind of confused, but I use like at my job, I used Jenkins before.
Okay.
And it's kind of similar, but it's not as new as GitHub, I think.
Oh,
It's
I mean,
older
Jenkins
process.
is sort of more like I would think of it more like a build system.
Yeah,
Right.
like we just deploy our code to it and it runs, and then the QA team runs and tests the code.
Right.
But
So, yeah, I mean,
this is like doing it all in one.
well, yeah, and this has the code, and in fact, if you look at let me show you one of my private projects. I can figure it out where it got to. I want me, not that one. And that one. So they've introduced this thing called actions, which lets me do two things. So there's two things. There's take a number certain, which is whenever I commit to the repository, it runs all my unit tests. And I think I got rid of all the red ones. Up, right? So that means that the unit tests fail. Right? If it's green, everything's okay. The other thing it lets me do is this only runs it in GitHub. My code is usually deployed on an AWS server. So it also lets me have another workflow, which I can just press a button and say, deploy it to the server. And again, it does some tests and if it's green. So this is more like what Jenkins does.
Yeah.
Right?
Yeah. But it's like, that's kind of like all it does.
Right.
Like GitHub does a lot more, so.
Right. And I mean, it is all new, but I think it's worthwhile learning. It is pretty popular around a lot of places. And you will have problems. Don't forget, it's not going to be easy. So, but just hang in there. Get me on either email or Discord, whatever, to sort it out if there's something you can't resolve.
Okay. Thank you.
You're welcome.
Professor, you said you can hand in lab 7 like whenever we get it done, right?
Pretty much. I think I said it was sometime in December, but let me just check what I actually.
Well, yeah, well, if that's the case, then you can answer my question. So you just need to find out how grades are good?
Basically, yes.
Alright. What about the assignments you give today for the GitHub?
That's due next week. Okay? At least the first cut. It's not going to be finished next week, but the first cut I want to be done next week. Okay? In fact, the due date is down as today, but let me change that. for Lab 7, but I don't think I set a close date. No, I haven't set a close date, so it doesn't matter. That's all I'm going to do. I think everybody's going to be late, so it's not going to be a discriminator in any way. I've said if you don't get it in by the original due date, I'm just going to use it to, maybe if you're really close to a grade boundary, if you've got it in before, I might bump it up and bump it down, depending.